Welcome to homework.
Okay, so we've got tin nitride, SN and N. And we know it's tin 4 plus. Well, nitrogen, when it forms an anion, is 3 minus. Okay, which means that we're going to need 3 tins. It's going to be tin 3 and 4 nitrogens to even out, right? We need to have a 12 plus charge if we have 3 of these, and we'll need 4 of these to have a 12 minus charge. That's the lowest common denominator that they can possibly meet at. Okay, so our next order of business then is finding out how many moles of tin and how many moles of nitrogen we have available to react, so we can determine what our limiting reagent is. Okay, so we're told that we have 2 grams of tin. Okay, so how do we determine how many moles of tin we have? Well, we divide 2 by the molecular weight of tin. Okay, so the molecular weight of tin is 118.71. So 2.00 divided by 118.71 tells us that we have 0.01685 moles of tin. And by the way, SN is the atomic symbol for tin. It's weird, but whatever. Okay. Now we also know that we have 340 milliliters of nitrogen. Okay. That's to say that we have a volume of 340 milliliters of nitrogen. And to answer this question, we're just going to have to assume that we have an ideal gas so that we can use PV equals nRT and find out whatever N is because we're told we're at standard temperature and pressure. Okay, so N is going to be equal to PV over RT. We know what volume is, we know what pressure, temperature, and RR. Okay. Now we will note that we've got this currently in terms of milliliters, but we may want to consider that this is also 0.340 liters, right, of nitrogen, so that when we use our gas constant, right, we can say, okay, well, this is, the gas constant can be written as, okay, so 1 atmosphere is the pressure. The volume is 0.340 liters. Okay, then the gas constant we want to use is 0.08205 liters per atmosphere, or liters times atmosphere per mole per Kelvin, right? And then we put the temperature in Kelvin. Standard temperature and pressure is going to be 298 Kelvin, right? And the reason for that now is that liters will cancel, atmospheres will cancel, Kelvin will cancel. We'll be left with 1 over moles, which is the same as just saying moles. So now we should be able to put this directly into a calculator and say 1 times 0.340 divided by 0.08205, 298 in the denominator as well. And we get 0.1391. 0.01391 moles of nitrogen gas. Okay. I'm going to write this in black instead. 0.01391 moles of N2. So what's the limiting reagent? Well, we have less nitrogen gas than we do tin, but recall the formula here, right? We need 3 tin for every 4 nitrogen. So one way we can kind of quickly do this is say, okay, well, how many units of 3 tins do we have, right? So we take our 0.1685 and we divide it by 3 and say that's how many moles of SN3 we have, right? So 0.01685 divided by 3 means that we have 0.00561 moles of SN3. And we can do the same for N2, right? We've got N2, but we need to know how many units of N4 we have, right? So we'll have to divide that by 2. 0.01391 divided by 2, and we will get 0.006955 moles of N2. Okay, so truly, actually, I mean, it didn't look like it, but the limiting reagent is actually the tin. And what that means is if we have 0.005617 moles of three sets of 3 tins, that's as much tin nitride as we're going to be able to get, right? The tin is our limiting reagent, and this is exactly how many moles of tin nitride we expect, right? And finally, we need to know what the mass of that tin nitride is that will form. So we're going to get 0.005617 moles of tin nitride. Okay, so altogether 0.005617. And now we just need to multiply by the molecular mass of tin nitride, right? So the molecular mass of tin times 3, right? So that's 118.71 times 3, plus the molecular weight of nitrogen times 4. So that's 14.0067 times 4. So ultimately, we get 0.005617 times 118.71 times 3 plus 14.0067 times 4. And we will get 2.315 grams of tin nitride.